right, so I will be starting this exam hack series on Pure 2. This will be the first video. Will set this up in a similar manner as I always do to go through this stuff. The first question or style of question will be on the logarithm and exponential question. And really all you need to understand here is what exactly is an exponential and a logarithm. Because exponentials actually, they turn up all the time. They're very common, and there's actually a profound reason for that. It's because, like, if you have the graph, so exponential, by the way, exponential is just, it's an irrational number. It's 2.71, blah, 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 forever. It's an irrational number. But if you take the derivative of this exponential, e of x, then you get e of x. And also if you integrate e of x, you get e of x. And that's actually a very peculiar thing and only happens with this function. That's why it turns up all the time. So that basically what that means is that if you have the graph of this green one of y equals e of x, then at the point, let's say, I don't know, let's say x is 1, so e, at that point e, the gradient is also e. So the gradient, the tangent line, is also equal to the value of y. And same goes for this area. So at the value of like e, under that area is also going to be e at that point y, which is very, very strange. And that's just an interesting side note. You don't actually need to know why that's strange, but the derivative and the integral of e to the x is e to the x, which is a strange thing. And those are the graphs, what they look like. They're the inverse of each other. So if you take, let's say, e, and we'll go through this, but e to the power of ln of x, that's just x. The fundamental relationship between logs and exponents is this. And I guess I'll just go to my iPad. So this is your fundamental relationship. This is how they relate to each other. Because basically logs are just used, all they're used to do in terms of what you need to do, is all that you use to do is solve equations, let's say, I don't know, like 10x equals 100. That's actually very easy, right? Because you know that x will just be 2. But what if it wasn't equal to 100? What if it equals, I don't know, 17? Well, now that becomes very hard. And what you say is, well, this thing is of this form. It's the same, these are the equivalent, they're stating the same thing. It's asking you, so it would be log, this would be log to the base 10 of a, which is 17, that equals x. So this value x will equal this if you plug it into your calculator. And so all that's asking, like let's say with that simpler example, with 100, all this is asking here, this log is asking, okay, what to the power of, 10 to the power of what, 10 to the power of what gives you 100? That's what that's asking. And that's all it really is. I mean, it's actually a very complicated thing, but in terms of what you have to know, like that's all you really need to know. That it's just asking, by taking this log to the base 10 of 100, you're asking what value, 10 to the power of what value equals 100? Or if it was a different one, it was 200. 10 to the power of what value gives you 200? And that's, as we'll see in the future, that's why, I'll say it later. But yeah, okay, so we'll go back to the math screen. And so if you know that, if you understand this relationship between exponents and logs, then all you need to do is know the logarithm rules. There's basically 3 rules: the product rule, quotient rule, and power rule. I have gone ahead and proved all of these rules for you in this theory. You don't actually need to know that. That's just kind of extra grounding to where they come from. But they really just in general come from, in a simple way, they come from these exponent rules. You know, these log rules, if you have something m times something n, and you take the log of that, that's the same thing as saying log of m plus log of n. And the same with division, it just equals log of n minus log of n. And with the power rule, log of m to the power of some n, just you can drop that power down and say n times log of n. And this really comes from these exponent rules, which you can see here. That's really it, and you've got the proofs of them there. But we will apply these rules significantly when we go through questions, and I will explain them in more detail. But other than that, we should go through questions right now. All right, let's jump into the questions. Okay, so as I said before, these logs are used to solve equations where the x's, or the unknown variable, is in the exponent. So, for example, with this one, we want to solve this. 6 2x minus 1 equals 5e 3x plus 2. It's also important to note that I will be using, and you probably should use it too, you should always use the natural log of x to find these things. And it's just the same thing, but to the base e. This becomes very useful when we have to deal with these things, because in fact I'll show you in a minute. So you take the natural log of both sides, ln of 6, 2x minus 1, equals ln of 5, e 3x plus 2. Now you can't just take the 5 out. You can't just do that, because this is a log. It's applying to that entire function, 5e to the 3x plus 2. So we can use the product rule here. This thing on this side will be ln of 5 plus ln of e 3x plus 2. From that product rule on the theory sheet. Those three rules, the product rule, the quotient rule. So when you're timesing two things in a log, when you're dividing two things in a log, and then the power rule, when you have a power in the log, which we'll use here. The power rule, you can just drop this exponent down. You get 2x minus 1 times ln of 6. Right, and then we continue here. We can expand this stuff in. We get 2 ln of 6 x minus ln of 6, so we just expand that in, equals to ln of 5 plus, again using that exponent rule, plus 3x plus 2 of ln of e. Now this is why we use this thing, because this is equal to 1. Because basically what this is saying is ln, which is log to the base e, of e equals what? Well, that's just going to be, that's saying, like I said before, it's the same thing as saying e to the power of what equals e. And that's just going to be 1. E to the 1 equals e. But this could be for anything. So you could have log to the base b of b, or what, anything, any number to the power of what gives you b again. Well, it's going to be 1. So these things always equal 1. But let's say, for example, we wanted to know of 1. Well, this is a similar thing that pops up. Well, this is saying e to the what gives you 1. Well, this thing is 0. This equals 0. Right? Anything, this could be b, so b could be anything. Anything to the power of what gives you 1 is always going to be 0. That's just a side note. Anyway, okay, so therefore we get 2 ln of 6x minus ln of 6 equals, this is 1, so we get ln of 5 plus 3x plus 2. Right, we'll take this over, we get 2 ln of 6x minus 3x equals ln of 5 plus ln of 6 plus 2. Taking x out, we get 2 ln of 6 minus 3 equals ln of 5 plus ln of 6 plus 2. And then finally, we'll get x equals to ln of 5 plus ln of 6 plus 2 over 2 ln of 6 minus 3. Right, you could just plug that into your calculator, but in fact, these things can be made simpler, because ln of 5 plus ln of 6 is the same thing as saying ln of 5 times 6, which is 30, which is ln of 30. And this thing here will just be the same as ln of 6 from the power rule squared, which will be 36. So just to make it look a bit easier to plug into your calculator. ln of 30 plus 2 divided by ln of 36 minus 3 gives you 9 point, and it wants it how many significant figures? 4. So 9.256. 1, 2, 3, 4 significant figures. And that's your answer. It's the 4 significant figures. Right, so what you're doing here is you're applying logs to this so you can bring these unknown variables down and then solve the equation. The real thing here you want to remember is that log to the base b of anything of that same thing, is 1 through the logic I just said before. Okay, so that was 1 if we have an exponential, if they're to the exponents. Now what if we just get a straight up log 1? Well, it's going to be pretty much very similar. Okay, well, this is the quotient rule, so these things can be merged together, and we can say 2x plus 1 divided by x minus 3. It's from this rule. M over n equals ln of m minus ln of n. Right, so those two things we equal that. So that equals to 2. Now the reason you do that, the way to do this, when I was really young, what I used to do is I used to think, okay, we have an e here. You push this over, bump this up, and then you just drop this log, which will give you, 2x plus 1 over x minus 3 equals e squared, which is correct. But what you're actually doing, if it's mathematically logical, what you're actually doing is you take e to the power of both sides. You're going e to the power of ln of 2x plus 1 over x minus 3 equals e squared, which you can do. You just take an e to the power of both sides for e. And then so now e to the ln of x of anything is x. Because the exponential and the logarithm, they're inverse of each other. So when they're applied, they kind of cancel each other out. And so this is also a very important thing to remember, or to know, which makes sense. I mean, if you just look at those graphs, you've got this one looks like this, and this one looks like this on the worksheet. This is your y equals x. This is e of x and ln of x. They're reflected in the y equals x line, because they're the inverse of each other through a certain line. Anyway, so with this, then you get 2x plus 1 over x minus 3 equals e squared. What is it, 1 here? Let's solve this in terms of e. Okay, so we get 2x plus 1 equals e squared of x minus 3, which will give us e squared x minus 3e squared. Take that over, we get 2x minus e squared x equals to minus 1 minus 3e squared. Divide through by -1, you get e squared x minus 2x equals 1 plus 3e squared. Or not x squared, e squared. Take out an x, you get e squared minus 2 of 3e squared plus 1. So your x equals, in terms of e, is this. Okay, so it's basically the same thing. All you're really doing with these questions is you're just using those log rules, which I've proved and shown on the theory sheet, to solve these exponent and logarithm equations. And finally, the last real style that they like to do is a lot of times if you get some equation like this, it can actually be expressed via logs into a straight line. It can be transitioned into a straight line. And so with something like this, so you have this, y equals a of e, a minus b of x. Where a and b and constant, the graph is of ln of y, so that's important. It's ln of y versus x. Straight line passes through these points. So we have these points here, 0.4, 3.6, and 2.9 and 14.1 that line passes through. So this graph is a straight line. Remember, the straight line is y mx plus c. That's of its form, of that form. But now we have, instead of y versus x, we have ln of x versus x. So this would be ln of y equals mx plus c. So if we can transform this thing, this y, into this form, then we'll be able to find our a and b. So if we take the log of both sides, and then ln of y equals to ln of a from our product rule plus ln of e to the a minus b x. We can drop this down. A minus b of ln of e. A minus bx is x. Dropping this entire thing down. And that power rule of ln of e. That is 1. So therefore we get this final equation of a minus b of x plus ln of a, which is of that form ln of y equals mx plus c, what we wanted before. So this is our gradient and this is our y ln of y-intercept, so where x equals 0. You could do it like that, so you could plug, and I think I do it like that in some of the other questions. You can just equate this thing to the gradient, equate this thing to the y-axis or ln of y-axis intercept. But another way to do it is just you use these points, you just substitute these points in. So for the point, let's say, for the first point, 0.4, 3.6. So for doing something like this, you need to get two equations, because you've got two unknowns, so you need two equations relating those unknowns, and then you can find them. So substituting the point, and remember this is x ln of y, this point, not xy. And so if you substitute that in, you get, well, this is going to be 3.6 equals a minus b of 0.4 plus ln of a. Right, and so if you write it, I guess nicely, it'd be like something like this. 3 of ln of a of 3.6 minus ln of a. So that's one equation. And for this point, 2.9, 14.1, 2.9, 14.1. At that point, we get, this is, remember, this is ln of y, x. So it'll be 14.1 equals a minus b of 2.9 plus ln of a. And get it of that same form we did before. We're equal to 14.1 minus ln of a. And that's our second equation. Now, in order to solve this, what we do, I mean, you could actually, I mean, there's many ways you could do it, but I mean, the way I would do it is you would do, okay, you need to figure out, okay, so if you want to do like, basically, you ask yourself, so you want to somehow get rid of this a minus b, and then you just get an ln of a, something of ln of a. And to do that, you say, okay, so how many, so 0.4 times what goes into 2.9, so 2.9 divided by 0.4, that's 7.25. So if you say equation 1, so 1 times 7.25, because that's going to give you a 2.9 here. I mean that, okay, I guess I'll just show you that. So that this equation times 7.25 will give you a minus b of 0.4 times 7.25 is 2.9 equals to 3.6 times 7.25 is 26.1, and ln of a times 7.25 would just be minus 7.25 ln of a. Now you do this equation, this 1 times 7.25 minus equation 2. You do that because this is going to get cancelled with this. So when you do that, that minus that is just 0, equals to 26.1 minus 14.1 gives you 12 minus 7.25 minus 1 for the ln of a will just be minus 7.25 plus 1, which would be minus 6.25 ln of a. So that gives us 12 divided by, so ln of a equals to 12 divided by 6.25. Which gives us ln of a equals 1.92. Therefore, a equals e to the 1.92. Oh, this is from before. Because my computer crapped out. So annoying when this happens. Craps out and then I have to redo the question. Bloody OBS. Okay, so now you have this a. Now you can just substitute that value into, let's say, equation 1. Into equation 1 to get b. So this would be e to the 1.92 minus b times 0.4. 0.4 equals to 14.1 minus 14.1 minus ln of a was just 1.92. Oh, not 14.1. 3.6, sorry. $3.6. Okay, so you get 0.4 e to the 1.92 minus 0.4 b equals 3.6 minus that is 1.68, which gives you, will be 0.4 b equals to 0.4 e to the 1.92 minus 1.68. So divide on that side, 0.4. So you get a b of that. So our a is, if you just plug this exactly into your calculator, so shift e to the power of 1.92, 6.82. How many significant figures do they want? 3. So 6.82 is a. And if you plug all that in, so times 0.4 minus 1.68 divided by 0.4 is 2.62. And b is 2.62. And those are your answers. So that's really when you're translating between this exponent or exponential or something into a straight line. They have questions like that style a lot on the worksheet as well. But that's all the styles. That's really all they can ask you. All you need to do is you need to understand the log rules, understand what a log and an exponential actually is. They're just the inverse of each other, and you're basically good to go. And that's it. All right, now I'm going to probably talk deeper and try to give these ideas some context in terms of your own life and in terms of actual existence. Just deepen them as ideas and not just for an exam. Okay, so really the biggest idea that you've been introduced to here is the idea of an exponential. And this exponential, it pops up everywhere in all these laws, in all these equations. It keeps popping up. It's kind of like pi. It pops up all the time, this irrational, large irrational number. When we try to formalize the universe into laws, into mathematical equations, this exponential, even imaginary, it comes from this guy called Euler, or Euler, I think is how you pronounce it. So if you're interested, you should look him up. He's a weird guy. It pops up all the time. So you have this way, we're trying to represent the world into some sort of logical system. And then through doing that, we get these irrational infinite numbers. And so there's really a few ways to look at this. One of the ways is, okay, exponential growth seemingly is a deep underneath the surface of everything in your world that you're seeing. There's this exponential component to it, which means things grow exponentially, means they rapidly grow faster and faster and faster and faster. And so for you, in terms of your own life, you should, as a personal kind of note, you should look for things which basically tap into an exponential growth for you. So you should be acting in a manner in life in which when you're doing something, your growth becomes exponential. That's just a side point. It's kind of a little bit of advice, because with all of this stuff in mathematics and in physics, I always tend to say that we want to live in accordance with what nature is presenting to us on the deepest level. So if on the deepest level, this exponential, or even with pi, this circular thing pops up a lot, then you should try to emulate that in your own life. But aside from that, let's just think about that as an actual thing. What a strange thing. You have this infinite, completely unique, it goes forever number, 2 point whatever, forever. Like that thing keeps popping up all the time. It pops up everywhere. So you have this kind of infinite number which pops up in the most logical systems that we can create. And what does that actually mean? I mean, that's very, very strange that that happens. I mean, why would that happen? I mean, you look around you and you can describe these sort of this universe in certain ways. And then all of a sudden, this exponential, this infinite irrational number pops up all the time. So there seems to be, for me, that says there always seems to be, and this keeps popping up, there always seems to be this infinite nature to reality. Is that no matter how we try to systemize it, understand it, or make it logical, this sort of infinite just seeps in everywhere we look. There's this infinite nature to the universe. And just in terms of the universe, I mean, it is, by our observation, infinite. It goes forever. It never ends. And the same goes with mathematics and this stuff. There's this infinite nature to it, where even in this exponential number, it's an infinite number. And it just doesn't end. And that's very, very strange. There's really this infinite thing about the universe which just won't stop. It won't stop being infinite. The goddamn thing won't stop being infinite. And so with exponentials and exponential growth, I mean, you even look at like there's certain aspects of the universe, it's like where you go and where you look, or like a black hole or something like that. Like there's an exponential thing to it where it just rapidly increases, far like the gravitational pull, whatever metric you use, like there's a rapid increase the closer and closer you get to it. It's so rapid, in fact, with like something like a black hole, it literally tears the fabric of physics, and it just stops, like it rips apart even the mind things that we have. It just tears it apart. There's this rapid nature to life and to existence, in which, like, depending on what you are, you either become kind of stagnant and you kind of reach a stabilizing point, or you go into an exponential growth or an exponential decline, and where there's a rapid expansion of your being and of what you know and who you are. And also, I would say with this exponential thing, you as a being, whatever you are, if you track your consciousness, this awareness that you have, and you push it back into yourself, you're actually going to find that also within you is this infinity. There's an infinite thing in you in which you can keep pushing back. And it just exponentially gets deeper and deeper and deeper and more profound and more mysterious and more strange. And it deepens and deepens you. And really the kind of people that you want to be, and you want to call it kind of like emulate, or the attitude you want to have, is you want to deepen everything in your life through your schooling. It's like you want to be looking at the ideas that have been found. You want to see the people that found them and have created them. You want to understand them, and then you want to emulate it in your life to the point where you deepen your experience of life, you deepen your experience of existence, and you deepen your understanding of what is happening. And that's really, for me, if I'm just talking kind of just off the cuff here, is what this exponential thing, or these irrational objects in mathematics like pi, exponentials, these kind of things, what they really represent. They represent some sort of infinite, like underneath everything, underneath even just your physical, like if you go into yourself and your being, like underneath it all, there's this infinite kind of thing which can be exponentially explored. And that's really the beauty of it. And I believe that also the understanding, like whatever that is, the phenomenon of you understanding things, this is also exponential. And so it will rapidly increase if you continue to have this attitude. I feel it with myself, like there's this exponential growth in my understanding of what is happening in terms of the entire universe. Because I've been learning for so long, I've been reading for so long, I've been contemplating for so long, I've been writing, I've been producing, I've been doing all this for so long. There's this inner exponential growth of understanding. And that is a really profound thing which you as a human being can tap into. But yeah, I mean, that's just a little talk on it at the end. And I'm really, really trying my best here to reconnect people with this sense of profundity and this sense of mystery and this sense of just intrigue. It's like, these are not dry, abstract, but just purely abstract ideas to be used to pass a test. These are profound ideas that have been found and have been used within society to push us forward, to make us understand more, and to really give us a profound connection to what is happening, what could be happening, what isn't happening. Like, it deepens your experience of life. And that's really what you want. You want to deepen your experience of life. You want to deepen your experience of yourself. You want to know yourself more. You want to know the universe more. And by doing that, you will only become more and more engaged in life. And it won't be this sort of mind-numbing, you're just going through the motions kind of thing. You don't want to get stuck in that cycle of just this mind-numbing thing. And maybe that's even where pi comes from. It's like getting stuck in that circle, that constant cycle. And maybe on the grand sense, something like pi is actually very interesting, because there is these cycles that we go through when we grow exponentially. We go through these cycles, and then we jump to a higher cycle, and then we jump to a higher cycle, and we're moving through life and our experience of life exponentially growing and understanding exponentially more. Anyway, that's it from me. This will be the first video of this series. I plan to do all of these videos for Pure 2 and to make it very clear, these ending talks, to try and deepen your understanding and deepen your sense of profundity about life, existence, mathematics, the law. Because that's really the place which I live in. I from a day-to-day basis, I live in a very strange world, because my world is basically has an underneath it all is very strange to me. Nothing actually really makes sense to me, even though technically extremely intellectually inclined and know a lot intellectually. But by doing that, I've actually found out that I know nothing. But that's it from me. I hope you're all well. I hope this video was useful. Any questions, the worksheets will be in the description. Links for that, you can download that. Any questions, any queries, questions about anything, questions about the exam, about mathematics, about the theory, even about existence itself, I will be happy to answer those things. I am here for you. I do this for you. Goodbye.